Oh, so today I will be talking about the direct product. So first, what is the direct product? So the direct product. Okay, so the direct product, usually denoted with an asterisk, which is a binary operation, and it combines two small groups, G1 and G2, into a larger group. So basically, how it works is that G1 and G2 can be any group, can be finite group, infinite group, abelian, non-abelian, doesn't matter. And so the G1 and the direct product of G1 and G2 will be equal to X and Y are pairs of numbers X and Y such that X is an element of G1 and Y is an element of G2. So this is the direct product. And so if we do the group operation for direct product, let's say X and Y times A and B, that will equal X times A, Y times B, and the identity element will be E1, the identity element of G1, and E2, which is the identity element of G2. So that will be the identity. So that is basically how the group products are defined. I mean the direct products are defined. So let's take a look at an example. Let me clear my screen. Okay. So let's say G1 is the integers under addition. And G2 will be the four roots of unity, 1i, -1, -i, under multiplication. So if we want to take the direct product of two elements in this group, let's say 3 comma I times 4 comma -i. The first element the first component will be the element of G1 and the second component will be element of G2. And that will equal, we perform the respective operations for each component. So let's say that would be a 3 plus 4 because the operation of G1 is addition, and I times -i because the operation for G2 is multiplication. That would be give us 7 and 1. I times -i 1. So we just took a direct product of these two elements. And the direct product is satisfies all the axioms of groups. So we, in this case, the identity element will be 0, 1 because 0 is the identity element of G1 and 1 is the identity element of G2. So to prove that it is the identity element, let's say X, Y times 0, 1 will get X plus 0, Y times 1, which is X, Y. We get the same thing. And if we do the reverse order, 0, 1 times X, Y, we'll get 0 plus X, 1 times Y, which is X, Y. So we have proved that it is the identity element. We can also check that it satisfies some other property, like for example, it has inverse. That's another axiom of group. So in this case, we're still using the same example, X and Y. The inverse of X and Y will be equal to -X and 1 over Y. Actually, let me do explicitly the inverse of X and the inverse of y. The inverse of x under addition, which will be negative x. The inverse of y under multiplication will be 1 over y. And to prove that it is the inverse, x comma y times negative x comma 1 over y, we get x plus negative x y times 1 over y, which will be 0 comma 1, the identity element. And we do it the other way around, negative x comma 1 over y times x comma y, we get negative x plus x 1 over y times y, which is 0 comma 1. So we end up with the identity element. So it satisfies the inverse axiom of group. We also have got the associative axiom. So let's see if we can prove that it also satisfies the associative property. So again, all right, let me change my color just because. So we have AB, X, Y, and MN. These are 3 elements of the direct product. And so let's see if we can make it satisfy the associative property. AB times X, Y, and then we multiply by MN. What do we get? That will be A times X, B times Y times MN. That will equal A times X times M, B times Y times N. And we do it the other way around, A, B times the product of X, Y, and N will be equal to AB times, we take the direct product, we get X times M, Y times N, which is equal to A times X times M, B times Y times N. And as we can see, this and this are the same. So it satisfies the associative property. And we also have the closure property, but I'm not going to try and prove that right now. But it satisfies the closure property. So it is a valid group. We can also take the direct product of more than 2 groups. For example, let's try taking the direct product of 3 groups. G1 times G2 times G3. Then the elements will be X, Y, Z. Check that X is an element of G1, Y is an element of G2, and Z is an element of G3. And the identity element will be E1, E2, E3, where E1 is the identity element of G1, E2 is the identity element of G2, and E3 is the identity element of G3. And one can take the direct product of any number of groups, even an infinite number of groups. But that's kind of a bit difficult to think about. Let me do an example with the direct product of 3 groups. So let's let G1 is equal to the integers mod 3, G2 will be the integers mod 4, and G3 will be the integers mod 5. Then we can see that the order of G1 is 3. The only elements are 0, 1, 2. the order of G2 will be 4, 0, 1, 2, 3. And the order of G3 will be 5, 0, 1, 2, 3, 4. Order of G2 would be 4. And order of G3 will be 5. And if we have defined G will be equal to the direct product of G1, G2, and G3. Then the order of G will be equal to the product of the orders. So the order of G1 times the order of G2 times the order of G3, which will be equal to 3 times 4 times 5 or 60. Okay, and using this as an example, let's do an example, because it's the element, because it's the integer mod 3, the integer mod 4, and integer mod 5, we have to take element. The values have to be elements. Let's say 2, I don't know, 1 and 4, and we could say 2, 3, and 3. Then if we, because the operation is addition, so that is 2 plus 2, 1 plus 3, 4 plus 3. Then 2 plus 2 in normal addition is 4, but since we're taking the integer mod 3, 2 plus 2 will be equal to 1. So 4 is equal to 1 mod 3. 1 plus 3 is 4, which is equal to 0 mod 4. 4 plus 3 is 7, which is equal to 2 mod 5. And so this will be, we have just taken the product. And the order of G can be infinite if, let's say we have G1, let's say, let me do this. G1 is equal to, G is equal to G1, the direct product of G1, G2, G3, on and on. If there's an infinite number of groups, then the order of G will be infinite. But if it's a finite up to Gn, then the order of G will be equal to the product of each in the respective order, G1 times G2 up to Gn. And if any one of these groups is infinite, then the direct product will be infinite. And if any one of these groups are non-abelian, which means they don't satisfy the commutative property, then the direct product will not satisfy the commutative property. But if every single one of these groups are abelian, if and only if every one of these groups are abelian, G will be abelian. Okay, and we also have an interesting fact that we have to prove. Let's let X and Y be the element in the direct product of G1 and G2. And let's say the order, what do we call it? The order of X will be equal to R, and the order of Y is equal to S. What does it mean for to be an order of an element? The order of an element is the smallest R such that X to the power of R is equal to 1, which means when we repeatedly apply itself, it will eventually reach not 1, the identity element. For example, let's let X be equal to 2 and our group equal to the integer mod 6. Under addition, then the order of X will be equal to 3. So 2 plus 2 plus 2 will be due to itself 3 times, which in normal addition is 6, which is 0 mod 6. So the order is 3. All right, and so now we know what the order is. Then if we have this property, then the order of X and Y, the order of this group will be equal to the least common multiple of, let me rewrite that, that's terrible, LCM of R and S. And we can prove it by letting L is equal to the LCM of R and S, which means by the definition of LCM, there are two integers, A and B, such that R times A is equal to L, and S times B is also equal to L, where A and B are natural numbers. Then we can say X and Y to the power of L will be equal to X to the L times and Y to the L, which is equal to X to the L, in this case would be RA, and Y to the SB, and let me get myself some space over here, which will be also be equal to X to the R with the power of A, and Y to the power of S to the power of B. And since we know that by the property of exponents, we know that X to the power of R is equal to 1, the identity element of G1. Let me call it E1, to the power of A, and E2, the identity element of G2 to the power of B. That will be equal to 1, 1. Well, E1, E2. And so we have proven that that the X, Y, the order of X and Y must divide L. And I can prove the converse of that statement too. So let me clear. All right, let me clear everything. Let's say that L prime is equal to the order of X, Y. So X, Y to the L prime is equal to E1, E2. Then, okay. So X to the L prime is equal to E1, and Y to the L prime is equal to E2. That means that R, which is the order of X, must divide L prime, and S, which is the order of Y, must divide L prime. Then that means that the LCM of R and S must divide L prime. So the LCM of R and S, which is just L, must divide L prime. And before we have proved that L prime, which is the order of X and Y, must divide L, and L must divide the order of X and Y. The only way that it can satisfy A divides B and B divides A is that A and B must be equal. So the order of X and Y must equal L, which is the LCM of R and S. And so we have proved QED. So that's a very interesting property of the direct product. As an analogy, the direct product is like the building block of groups, much like the building block of chemistry or atoms. And atoms can bond together in different ways, like ionic bond, covalent bond, metallic bond, to produce all these different things that we see around us today. The building blocks of biology of a protein are the 20 different amino acids. There are 20 different amino acids, and they can combine together to form countless proteins. And in the human body alone, estimates have it in the 10 to the power of 5 unique proteins. And so in number theory, the building blocks are prime number 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, etc. And they can combine together through multiplication to form all the natural numbers except for one, but that's okay. And the building blocks groups are simple groups, which are basically the prime numbers of groups. They can't be broken down further. And the direct product is one way that they can combine to form more complex groups. And one application of it is to apply that in the other direction to break up some groups into simpler groups. Although there are other groups that cannot be broken down using a direct product. And the direct product can also be used to prove the fundamental theorem of finitely generated abelian groups. Let me write that down. Fundamental theorem of finitely generated abelian group, which is that any abelian group that is finitely generated is the direct product of the integers, either the direct product of integers or the integers mod n for various n. And so that's one application of the direct product. So that's it. This is my presentation on the direct product.